So Dirk, is it okay if I start introducing you?
Absolutely, yes, please do.
Good morning, everyone. Good morning. We are very delighted to have Professor Dirk Pesch from Computer Science Department at the University College Cork in Ireland as our speaker today, this morning. He is with the School of Computer Science and IT over there. He leads research initiatives in a multitude of areas, most notably future networks, IoT, cyber physical systems, looking into different types of application in smart and connected communities, energy efficient buildings, sustainable cities, and smart manufacturing. I am very much familiar with his research areas, and we have collaborated in the past as well. He has visited ROLA a few years ago, and I have visited him as well. So we have a good connection with MST and UCC now. He was at the Cork Institute of Technology before moving to UCC. Professor Pesch actually leads quite a few large center-scale projects funded by Science Foundation of Ireland. And the famous one is the Connect Center for Future Networks and Confirm Center for Smart Manufacturing. He has been very prolific in terms of research and projects, has been organizing different conferences as program chairs or in different other capacities. And I don't want to go into all the details. You have seen his bio and in the talk announcement. He got his diploma in engineering from Aachen University, Germany, and PhD from University of Strathclyde, Glasgow in Scotland, both in electrical and electronic engineering. So without much ado, let us just give a big thanks to Professor Pesch. So Dirk, thank you very much for accepting our invitation. The podium is yours.
Thank you very much for the introduction, Sajal, and I'm delighted to be here and welcome everybody to my talk today. I hope it'll be interesting. Let me kind of reorganize all my three screens a bit so I know what I can see what I'm talking about. So today's talk touches on one of the areas where we have we have done quite a bit of work over the last 3-4 years, and this is particularly focused on low power wide area networking for the Internet of Things, in particular the LoRa wide area network standard. And some of you may be familiar with this. So just a little bit on an outline of the talk. I'll talk a little bit about connectivity for the Internet of Things, just to position LoRa and LoRaWAN a bit. Then talk a little bit about LoRaWAN for those of you who may not have heard about it, who don't know anything or much about it. Then I'll talk a little bit about some of the issues around it that we've been investigating, which is in particular scalability for LoRaWAN, and then I'll talk about some of the solutions that we've worked on, and finally some ongoing work that is currently under review with the IEEE IoT journal is focused on LoRa and satellite communications. So if we look at connectivity options for the IoT, there is a zoo out there. There is more than I can count almost. So we have a very, very wide range of connectivity solutions that's for the Internet of Things around machine-to-machine communication. And they're all characterized by kind of a different range of, or a range of different metrics. So for example, the range, so the distance over which they can operate, the throughput that they provide, the power consumption, etc. Something like the whether they operate in licensed or unlicensed radio spectrum, etc. And if you look at the different, and this is just a subset here, different solutions, one can perhaps, and this maps a little bit over here, over the kind of two of the key, I guess, metrics in terms of the range and the throughput that they provide. So we can see lots of those here, some based on cellular technology, some are around wireless, around long range. So long range, for example, which are the low power wide area networks. So for example, Sigfox is one of them. Weightless is a standard that you may not have heard about. It's not very prominent. Link Labs is quite interesting. There's a Symphony by Link Labs is using LoRa modulation with a standard that uses time slotted mechanisms. It's quite gaining momentum in the US, for example, whereas LoRaWAN is probably more prominent in Europe at the moment. There's some other technologies, and then things that you might have heard about, Z-Wave, Zigbee, for example, things you can thread, things you can buy in consumer electronics shops, for example. But if we look at those here, we can see that those areas, those technologies, for example, based on IEEE 802.15.4 on this standard, like Thread, like Wireless HART, like Zigbee, for example, like WiSUN, their range is quite limited. Here in this case, probably a little bit beyond 100 meters, could probably be stretched around here. And the data rates are relatively low. They don't go up to a megabit per second. And then we have all of these different 802.11, for example, which vary in range, but have higher data rates, for example. And then what is interesting for the talk today are the low power wide area networks. And these ones have low data, sometimes very low data rate, and but have a large range. And the range here goes up to tens of kilometers potentially, depending on the environment. But today I want to talk about LoRa and LoRaWAN in particular. So if we look at LoRa, LoRa is effectively a modulation scheme that was developed by a US company, well, developed by a French company that then was bought by a US chip manufacturer called Semtech. And so Semtech owned the intellectual property on the LoRa modulation, and they don't disclose all the details, although researchers have re-engineered this, so we know quite a lot about the LoRa modulation scheme and some of the functions of it. But the physical layer, which is the LoRa modulation, is embedded in, or is implemented in chipsets manufactured by Semtech, and Semtech are the only supplier of those. And so so if you wanted to implement a LoRaWAN, for example, you need to buy nodes and gateways with Semtech chipsets. However, on top of this, the LoRaWAN Association has developed and specified an open standard. And this open standard is kind of it's almost an end-to-end communication network for machine-to-machine communication. So we have lots of different types of sensors as the end devices, the user devices. And really what you can do here is to some extent limited by our imagination, like most of the IoT applications. Then we have gateways. And the gateways are like the base stations, for example. And in a way, this makes the LoRa network something like a cellular network, although each gateway can receive all of the nodes in its vicinity. So a node basically transmits data that can be picked up by multiple gateways. And then the gateways transmit over some back-end connectivity the data to a network server. And the network server is basically the control entity of the network that deals with medium access control, it deals with resource allocation, etc. And then from the network server to the network server are one or more application servers on which the actual IoT applications live. And LoRa supports an end-to-end secure communication payload protocol between the nodes and the application server. So that's kind of the structure of a LoRaWAN. And sometimes these LoRaWAN, and so on are used interchangeably often in the literature. But what is important to remember here is that LoRa is actually the modulation scheme, so the physical layer, and the rest is LoRaWAN. Although I might use the two interchangeably because LoRa is easier to pronounce than LoRaWAN. So it has a simple cellular type topology. It uses an Aloha-based MAC protocol, and I hope you're all familiar with what Aloha means, but I'll talk about that in a moment. It has different classes for different downlink profiles, but in our work, we have focused largely on the so-called class A, and it offers end-to-end security. So if we look at the protocol stack here, from a radio perspective, it operates an unlicensed spectrum. So in Europe, it operates in 2 frequency bands, the so-called ISM bands at 868 megahertz and 433 megahertz. In the US, LoRa operates at 915, in Australia at 430 and so on. So each region has its own through its communications commission or equivalent federal, the equivalent of the FCC, has allocated particular spectrum in which LoRa can operate. As I mentioned, the physical layer, the LoRa modulation is owned by Semtech, and then the LoRa Alliance specifies the MAC layer and the network operation, basically. And currently there are 3 profiles defined: class A, B, and C. Today, we're essentially only looking at the class E. But if you're interested, the LoRa Alliance has made the specifications available for download. So if you want to learn more about them, you can download them. And then applications are effectively proprietary. So everybody can implement their own applications. There are an increasing number of companies, particularly startups and so on, that are operating now in the LoRa space. In Europe, and I'm not sure how much it might be operating in the US, but in Europe, there is also a network called the Things Network, which is sort of an open access LoRaWAN network operated by the Things Network organization. But everybody can basically join them. You can buy a gateway or make your own gateway, with using a Raspberry Pi and a LoRa hat, for example. You can create your own gateways and connect them to the Things network. And the overall network server, the backend infrastructure, and so on is available. And for playing around with this, for trying your own home applications, for example, it's free. If you wanted to use it for commercial purposes, then you would have to pay something. Right, so the LoRa physical layer is based on a technology called chirp spread spectrum, which is a random change in tone frequency. So it's a kind of a form of frequency modulation during transmission. So effectively up and down chirps. So this is an up chirp here, and this is a down chirp. So this is the frequency, normalized frequency here. And if you look at a single chirp, you can see as the frequency here starts, the signal has a wavelength, a slow wavelength that increases. So it's like like an up chirp is like woo, and a down chirp is like woo. So this is kind of the way if you wanted to do it, an acoustic equivalent, and it's quite a robust modulation scheme. The payload is quite small. Worst case payload is about 59 bytes. And one of the significant aspects, certainly in Europe, and this varies with region and the unlicensed spectrum, but in Europe, LoRa has to observe a duty cycle of about 1%, which means that there is about 300 bytes per hour can be transmitted in the worst case situation. So a duty cycle of 1% is very little. It shouldn't be, for many applications, it's not a problem, because they are low power. They're meant to sense a little bit, wake up, transmit data, and then go back to sleep in order to operate like many IoT applications for long periods of time on a battery. However, the duty cycle also applies to the gateway. And that's a big problem, because the gateway, if the gateway needs to transmit more frequently, for example, sending acknowledgements for transmissions or any kind of other information for radio resource information, then that can become a very significant bottleneck for the size and the number of nodes that can be supported by a gateway. So on top of the chirp spread spectrum approach, LoRa allows for a number of spreading factors. So that means basically that the signal is spread out in time, and so different symbol. So each spreading factor has a different symbol length. And so if you look at here, these are two different spreading factors where you can see this one is normalized. And so this one here has about half the symbol length, for example. And this is a little bit like with other kind of like direct sequence spread spectrum, for example, different spread spectrum technologies allows parallel transmissions on different spreading factors. So a bit like direct sequence spread spectrum or CDMA, for example. So that's quite an interesting feature of LoRa modulation. And if you look at this here, the LoRa modulation provides for a number of spreading factors, from the so-called spreading factor of 7 to 12. And because the symbol length is different, a spreading factor of 7 spreads less than 12, which means that at a spreading factor of 7 can support a higher data rate. So in this case here, the data rate, for example, the physical layer data rate, roughly at a spreading factor of 7 on a 125 kilohertz carrier, is about just under 5.5 kilobit per second. Whereas a spreading factor of 12, which spreads out the signal more, only offers up to 250 bit per second, so a much lower data rate. However, if you look at this here, an increase in the spreading factor, while it means a lower data rate, it also improves the range. So it lowers the sensitivity of the receiver and therefore increases the range. So at a spreading factor of 12, you can transmit much further than with a spreading factor of 7, for example. However, the disadvantage as well is that because the symbols are longer, the same number of bits that are transmitted by a spreading factor of 12 have a longer air time. Apologies, my magic mouse is magic. Have a longer air time. So the transmission time is increased, and therefore the energy consumption. LoRa also supports a number of different transmit power levels, and it supports different coding rates. The coding rates, how exactly the coding works isn't disclosed by Semtech, but they quote a 4/5 up to 4/8 encoder. So 4/5 means 4 source symbols are transmitted as 5 encoded symbols, and 4/8 means 4 source symbols are transmitted as 8 transmitted symbols. And this then affects the actual bit rate, of course, that you can get from the bare physical bit rate to the bit rate that's available for user application. So, okay, what you need to remember is that with a spreading factor of 7, the airtime is reduced, the transmission range is lower, and with the spreading factor 12, transmission range is increased, but the airtime is also increased, so that the time it takes to transmit the same amount of data. So these different elements, like spreading factor, like coding rate, like power, for example, and so on, they are together called adaptive data rate mechanism in LoRa, and so these ones can be modified by the network server in order to optimize the network operation. So if we look at the performance, a brief performance look at LoRa here, for example, if we look at the airtime in milliseconds and the spreading factor, you can see, as I mentioned, on a bandwidth, the standard bandwidth is 125 kilohertz for a LoRa channel, but it could be 250 or 500 kilohertz. So these are options. But at 125 kilohertz, you can see how the airtime increases to transmit 20 bytes. And so this here is over 3000 milliseconds, so over 3 seconds. So that's quite a long transmission. And the energy consumption, as you can see, increases as well. Of course, with increased transmit power, it increases. But you can see how it's affected by the spreading factor, from quite small at spreading factor 7 to a significant amount at spreading factor 12. So that's the kind of a brief summary of the physical layer. But of course, LoRa allows multiple nodes to transmit to a gateway, and how do those nodes share the spectrum? And that's based on a very simple protocol called the Aloha protocol. And I presume most of you are familiar with it. In this case here, what a LoRa transmitter does is it wakes up when it has something to transmit, it transmits it, and this is what a kind of a LoRa transmission frame looks like, a preamble that allows the receiver to detect the transmission, then a header, payload, and a CRC check, an error correction check, basically. So transmission happens, then the LoRa the LoRa node then waits for, goes to sleep, wakes up, and opens a receive window during which it might receive a transmission by the gateway. So the transmission here could be an acknowledgement. If we have a confirmable transmission, for example, it could be a MAC command that requires changing of some transmission parameters, etc. If there is no, during the receive window, if there's no transmission, the node then goes to sleep again, wakes up for a second receive window, and might receive something here. So this one could be because the receive window here may not, the gateway may not be able to transmit here because of the 1% duty cycle, so the node might have to wait, and that of course costs power. However, because LoRaWAN uses the Aloha protocol, we might have 2 or more stations who transmit at the same time. So assuming this is the fixed packet length, you are probably all familiar that with Aloha. So during during a particular long interval, we can have only one transmission, and that interval, sort of in the simplest case, is governed by if we have a fixed packet length, by twice the packet lengths, because we can't have, before we start the transmission, every other transmission needs to have ceased, because otherwise, if you see here, node station 2 starts to transmit before station 1 has finished transmission, and we get a collision. And that, in that case, the gateway may not receive anything correctly. So the error check would indicate an error, and so on. And then we have a random delay. So you might be familiar, the throughput, you can calculate the throughput of LoRa, which depends on the packet generation rate at each station, and then the transmission time of a particular frame. And if we assume fixed frame lengths and so on, then it's quite straightforward to calculate the maximum throughput, and that's only 18%, and that's pretty poor. So, however, worse here is that also what we experience with MAC is also something called the capture effect. So what happens here is, because nodes are at different distances and potentially quite a distance away from a gateway, one node may be received because it transmits, it's closer by, or transmits with more power, for example. One node is received with a much higher signal or received signal level than another node. And so the capture effect works here, by which the larger the node received with more power drowns out the weaker submissions from another node. And so the problem with this then is, because we have different spreading factors in LoRa, what we have is that with a higher spreading factor, like 12, for example, we have a longer airtime. So the period during the vulnerable period during which we can have a collision increases. But also with a spreading factor of 7, for example, the nodes that use that tend to be closer to the base station or the gateway, because the gateway has a different spreading factor 7 has a different sensitivity, for example. So they tend to be closer and receive with more power than spreading factor 12. So what you can see is that nodes transmitting similarly at a spreading factor of 7, we have a lot less collision probability compared to a spreading factor of 12, because they tend to benefit from the capture effect, as well as their shorter airtime compared to a spreading factor of 12. So these are some of the problems that exist, and that really affects LoRa quite significantly in terms of the scalability, in terms of the number of nodes we can have, the coverage area, etc. So what we have done is we've kind of studied this problem a little bit more in detail. And so what we've looked at is we've looked at a number of different applications, for example. So what's the impact of this Aloha MAC on different applications? So we've looked at smart metering, smart lighting, smart parking, fleet tracking. So applications that need infrequent transmissions, but that need these kind of large ranges that LoRa offers, for example. So in smart city type applications. And so if we, then what we have looked at sort of different LoRa parameter settings. So we looked at these different IoT use cases using a LoRa simulator, which is quite a well-known simulator for LoRa. We assume a 20-byte payload, and the duration of each simulation run is roughly about a month, so to have sufficient statistical equilibrium. And the number of nodes, we varied between 200 and 1,000 in steps of about 200 nodes. So different parameter settings. So we picked up spreading factor 12, so which is the most robust, 125 kilohertz bandwidths, and a 408 channel coding. So this SN1, this kind of setting is the most robust. And then we varied this with others with different frequencies, with larger bandwidth, spreading factor 6, bandwidth 500, coder rate 4. This is the fastest possible setting where nodes can transmit very fast. And then we looked at different variations of this. So for example, SN5 is one where we changed the coder rate, for example, but we kept the rest. And if you look at the results here, so for example, smart meter, then you can see is at the different settings here, for example, you can see that some of them offer a packet delivery ratio of 100%. So they work very well. But others, for example, in particular, the setting that is recommended, for example, by the LoRa Association, which is SN1, best protection, etc. This one, you can see of how the packet delivery ratio drops very significantly when we increase the number of nodes. So we can actually, a gateway cannot support very many nodes in this case here. And we see similar effects with different types of application like street parking, street lighting, etc. And also in terms of the energy consumption. So we can see that the energy consumption also varies depending on the kind of physical parameter setting. And here we can see that the orange one, for example, doesn't perform so well, whereas those that can transmit very fast, they perform actually quite well. So let me skip over this here. So what we've tried to do is then, so we've analyzed the problem, we've seen difficulties for different types of use cases with scalability, etc. What we've then looked at, we've said, okay, how do we improve this? And how do we make sure that different types of applications and different types of users at different distances from a gateway can have a much better performance? So what we looked at here is in particular the fairness. And so we looked at a concept that we call fair adaptive data rate. And so that manages the data rate and transmission power levels for each node individually. So the network server would solve an optimization problem in order to give each, based on the information it has from the received information from each node, would try to find the best possible allocation of power levels and spreading factor, for example, in order to give everybody an equal chance at being received. And in this case here, so this is the optimization problem that's being solved by the server. And if you're kind of, I won't go into too much detail here, but if we look at some of the results here, you can look at this in detail at this paper that we published, part of IEEE WoWMoM a couple of years ago. And so if you look at the normal behavior in terms of fairness, and we looked at this earlier, between spreading factors 7 and 12, for example, then the 7 has a much lower collision probability compared to spreading factor of of 12. However, with our FAIR approach, where we're trying to balance transmission power, etc., across, we receive almost equal fairness. So the collision probability for increases for the spreading factors, the lower spreading factors. However, it improves very remarkably for the higher spreading factors. So we get a much better performance across for the whole network. And if we look at the fairness here, this is the fairness index we've used. I think it's based on Jane's fairness index. But if you look at this here, then we maintain a fairness of almost almost independently of the number of nodes. But if you look at the fairness, for example, on the standard LoRa, for example, it drops very much down when the number of nodes increases. And the way this works is by balancing the received signal level with a safe margin. So what we're doing is here we're changing over distance the power with which the individual nodes transmit. Now, some of this here, we have a zone here where we can't do too much. And the reason for this is that the power levels from LoRa, as you might have seen in slide 8, are limited to discrete values between 2 and 14 dBm. And so we can't just change it the way we like it. So we have to stick with those power levels. And so for this reason, we don't get perfect fairness, but we're trying to adapt the power to the sense with which each node transmits, to the sensitivity and the spreading factor and the distance. And so from this perspective is we actually achieve very good fairness. What it also, so if we compare this with other approaches, for example, so if we say we have, we use one channel, we transmit 80 byte packets, 5 per minute, and we simulate over or study this over 1 day, for example, then as you can see is the approach that we take here is we maintain quite a high fairness index, even when the number of nodes increases compared to others. And the two approaches we've looked at is by Reinders, Mert and Polin, and then by also compared to Bohr and Rödig. Utz Rödig is a colleague of mine in UCC. He's done prior work on this as well. And so if we compare this here, we can improve the fairness very significantly without sacrificing, without actually sacrificing the energy consumption, while maintaining, or while the number of nodes per gateway increases. So if we look then at the energy consumption here, this is the data extraction rate. So the data extraction rate, sometimes also called the packet delivery ratio. So we are maintaining the same performance of packet delivery ratio as the other scheme, the best other scheme, which is by Reinders and Polin. But if we look at with a small penalty in power consumption, because we need to tell each node that they have to adapt their data rates, spreading factors, and so on. So that's there's a small power consumption here, but we achieve much more fairness, and therefore a much better performance for the overall network, not only for nodes that happen to be very lucky to be close to a gateway. So if we now look at the MAC here, as I mentioned, the MAC is basically based on Aloha, and Aloha has limitations. And while we try to improve fairness and so on, ultimately we can't do anything about the high collision probability that LoRa carries, and ultimately the limited throughput. So how can we improve this? So one of the ways to improve this is to introduce some time-slotted operation. So to go away from the purely collision-based or purely contention-based approach, but to a more scheduled approach. And as you may know, is that there are plenty of other technologies, like, for example, the IEEE 802.15.4, which is used in many IoT and wireless sensor network applications, for example. There are different versions as well. As the standard one uses a carrier sense multiple access approach, so also contention based, but then there is also time-slotted a time-slotted channel hopping mechanism, for example, which is based on scheduled transmissions to avoid contention. And so if we basically say, okay, we have a LoRa physical layer, but now we try to change the MAC layer operation to a time-slotted mechanism, and that then reduces the number of collisions. However, the problem with time slotting, of course, is it requires synchronization, and that costs energy, because now we have additional transmissions between nodes and the gateway in order to manage the synchronization. And so what we try to do this in a very careful way, so that we ultimately the energy expenditure is returned to us in terms of saving energy for particular use cases that would otherwise suffer from excessive collisions and therefore retransmissions. So some of the motivation here for this was, which we looked at and which we studied, is bulk data delivery, and I'll come to that, and then also time constraint applications, which I don't talk about as much, but I have some of our publications, I've referenced them, where you can read up if you're interested in this. So if we look at this particular bulk data transmission use cases, one of the motivations behind time-slotted operations. So why would we want that? So imagine now you have a remote deployment of LoRa devices, for example, in a rural area, and there's very limited back-end connectivity. So one way of collecting data from those nodes would be, for example, by having a gateway associated with a drone, and the drone flies by perhaps once or twice a day, for example, and collects data. And of course, if the drone flies by and hovers over a field deployment of LoRa nodes, for example, if they were now all transmitting at once their stored data, then that would create huge amount of collisions using the Aloha protocol. That would be very inefficient. And so we would either it would take quite a long time and a lot of energy to transmit them all, or it would require some coordination between them. And so we've looked at how do we achieve this with some coordination. Okay, so the coordination in this case here is using some time synchronization mechanism, and then also building on our earlier work that we did with the fair adaptive data rate allocation. So we learned of how to make it fairer for nodes and improve the chances of node to transmit. We also looked at resource allocation in terms of data rates, channels, and transmission power, similarly as we did before. So here are a number of 4 papers that have explored this in different use cases. The second in particular, free paper, which we published January last year in the IEEE IoT journal, looks at this particular approach here. So we are specifying a time-slotted MAC protocol. We're managing transmissions in slots to mitigate collisions. We consider 6 parallel data collections, so 1 per spreading factor. So a typical gateway, a LoRa gateway, by standard should be able to receive on all 6 spreading factors from 7 to 12 in parallel. And so what we're trying to do here is, and in total it should be able to receive 8 parallel transmissions. So what we're doing is here, we are effectively creating a time-slotted mechanism on each spreading factor. And the difference in spreading factors here, as I mentioned earlier, is the difference in symbol lengths. So each of the frames have a different duration based on the spreading factor. And if we organize them very carefully, then with the possibility of parallel transmissions on different spreading factors, we can have multiple parallel transmissions. And what we are looking at here is a group acknowledgement for those transmissions that need a confirmable data. And what we do is we optimize the gateway duty cycle here, because the 1% duty cycle that the gateway has is still a limitation here as well. So if we look at how does this work, so the first one is a 2-stage joining and synchronization process. So in the first stage, we can join a data collection process, and we can optimize this based on, and so we kind of have a switch, if you want to, here, alpha, that is either 0 or 1, so we can optimize for energy consumption or optimize for data collection time. So depending on which is our objective here. And the first approach here which is a join request, join accept, and so on, achieves a coarse time synchronization of about 1 second. And then the next stage of synchronization here is disseminating the frame structure. So the first joining process basically means that the network server can collect, or the gateway with the network server, they can collect basically how many nodes do we have, what are their requirements, etc. And then it can optimize the amount of slots that are needed on each of the different spreading factors. So what it does is it kind of optimizes this and creates, allocates packet lengths, the number of slots per frame, and the guard times. And that then gets down to a time synchronization of 1 millisecond using the F settings command. It's a MAC command that LoRa supports, and that the base station then transmits and distributes the frame structure to the nodes. And then the nodes basically in bulk upload their data into this scheduled frame structure. So if we look at this here, if you look at a simple application of 20 bytes every 45 minutes, for example, confirmable transmissions, data collection once per day. So in total, we have a bulk transmission of 5.6 kilobytes per node. Doesn't sound very much data, but as you recall, the data rates are quite low. And if we look here at legacy LoRa, delayed LoRa, which means that what we're trying to do is we're trying to spread out the transmission to avoid collisions a little bit. And then we have the two different approaches, that the time synchronization approaches, either for energy optimized or for data transmission optimized. And we can see here is, compared to legacy LoRa, where the number of devices increases and the network energy just goes through the roof, where the increase here is much lower. So our time synchronization in effect buys us, actually, while the synchronization costs energy, the total energy consumption drops very significantly. In fact, by 720%. And if we look now at the data delivery ratio, for example, we get effectively perfect data delivery ratio, assuming a favorable wireless channel, compared to the LoRa standard one, where the data delivery ratio drops very significantly due to collisions and basically becomes completely unusable, even with a small number of nodes. Whereas our time synchronization approach here is really scalable because it maintains very good performance, even for a large number of nodes. And if we look at the data collection time, for example, then the delayed LoRa collection time is quite significant in terms of minutes. So the drone would have to hover around there quite a long time and so on. And that's often problematic because the drone is also battery powered, compared to our data collection times when we are energy optimized, which is a little bit longer, compared to collection optimized, which is faster. In this case, quite significantly faster. Okay, and then finally, the last bit I wanted to talk about is some work we've started recently in collaboration with colleagues of the Argentinian Space Agency and the University of Chile in Santiago, in Chile, is to kind of how to apply some of these ideas of time-slotted synchronization mechanism to LoRa using for satellite communication. So LoRa has a very significant link budget, and this has made it also attractive for satellite operation. And in particular, in situations where, like for example, with drones coming in, where we don't have a terrestrial back-end infrastructure to connect gateways to the internet, for example. One option, as I just explained in the earlier use case, was with drones, but here we might consider satellites. So low Earth orbit satellites that are not too far away, so that the LoRa link budget actually works. And so if we assume here, let's say this is a bit of South America, so we have a satellite flying over South America. This is our field of nodes, for example, distributed in very remote areas. And so we get this flyover of satellites, and during the flyover, we collect data from sensor nodes on the ground. So this could be bulk data delivery, although we haven't considered this, or it could be normal data delivery, for example. So if we look at this, is one interesting thing is here. Sorry, my Apple Magic mouse is behaving magically again. So here you can see different. If this is our deployment here, this is kind of the projection from the satellite trajectory, for example, onto the deployment area of the nodes. So this is kind of an immediate flyover, this is a pass-by, etc. So all of these kind of create, each individual flyovers of a satellite create different types of network topologies. And that's quite interesting, actually. And we don't get that as much in a terrestrial environment. So what we try to do here again is we try to have a time mechanism. So in this case here, we have a beacon. So the satellite flies over and transmits beacons, which allows the nodes to assess their range to the satellite, for example, and therefore kind of decide on which spreading factor should they use, for example. And then there is an uplink frame in which the nodes transmit using the LoRa Aloha protocol. And so if we look at the scalability here, so here we have actually compared the LoRa legacy. So this left one is LoRa legacy, which I've just explained. And then there's a new modulation scheme, which is just out, it's called LoRa enhanced. And this uses a time-slotted hopping mechanism. So it's kind of a little bit like what 82.15.4e did to the traditional 15.4. So here we can see different types of transmission opportunities. So this is LoRa-L conservative with the traditional Aloha. Then we have a random one. We have then one that tries to adjust to the trajectory. So to guess when it's the best transmission time, for example, then trajectory, but with random transmission. So this is a random transmission. This is trajectory, random transmission, and so on. So different types of transmission opportunities. And here we can see is that the average extraction rate and how this in effect is affected by the number of nodes per satellite. And so again, we have similar observations here that we had earlier. The top one here is a godlike view where the satellite basically has perfect knowledge of all the locations of the nodes and when they could transmit, and perfectly schedules the transmissions. Now this is purely theoretical. I mean, it couldn't be implemented, but here you have perfect operation, for example. But you can see is the different performance here. So again, we see this scalability impact. However, with the new LoRa modulation scheme, we actually get a much better performance here. But interestingly is, if you look at the random behavior, for example, then we actually, the trajectory-based approaches seem to work best compared to the traditional or random approaches. And so if we then, I might skip this here. These are kind of looking again at the average packet count, packet count that in terms of transmissions, and then the number of node counts here. And again, here you can see the number of sent packets. The extracted packets, for example, are quite low, but you can see different behavior based on the different transmission schemes, for example. But it suggests that LoRa in a satellite environment actually can work quite well. So in summary, this was just a kind of a whistle-stop tour of some of the work that we've done and that others are doing around LoRaWAN for the Internet of Things. It's an attractive connectivity solution also for satellite communications. However, the current standard suffers from a number of drawbacks, in particular the scalability of the MAC protocol. We've studied a number of solutions, improving fairness, introducing time-slotted approaches, and recently we've also looked at LoRa used in a satellite environment. So that's this, and I'd like to acknowledge a lot of contributions and work from some of my collaborators and former PhD students. So thank you very much.
Thank you, Dirk, for a very nice presentation. It's time for questions now.
Will I stop sharing so we can all see each other a bit better?
Yeah, please.
Yeah. But we can go back to if somebody has a
right. And Yeah, you can see a lot of uploads are coming, and anybody who wants to switch on your video, please feel free to do that. So time for questions. Kevin, do
So
you
I
have a
was,
question?
yeah, I was going to ask a question. So, I'm working on a smart farm applications and looking at different approaches to provide connectivity. And these are farms in rural areas, maybe very wide, very large areas, 200 meters in the state of Iowa. So, I mean, the alternatives seem limited based on, availability, RF, and other things. But in terms of LoRa, I mean, it wasn't one that was even on my list because, well, most likely it was. There were other ones that are higher. So, how when you talk about LoRa, where does it fit? Where does it fit in? Who's using it? Why would they use it? Why is it bubble up to the top in some of those applications?
Yeah, so so LoRa is depending on the environment. LoRa has quite a range, so in particular, if you look at rural areas, for example, large farms or so, if you have line of sight connectivity, LoRa at spreading factor 12, for example, can cover ranges of 15 to 25 kilometers, or maybe I should say this in miles. Sorry, I'm very metric in Europe, but so about you could say it covers easily 10 miles, at the highest spreading factor, if you have a very open environment and line of sight. So that's quite attractive. But there are others who offer this as well. Other technologies, for example. There's other, some of the other low power wide area network technologies offer this as well. I guess one of the advantages of LoRa is that it is open source. I mean, okay, you have to buy the chipset from Semtech, but that's only a small thing. But the whole infrastructure is open source. So you can buy, you can make, as I said earlier, you can make your own gateway with a Raspberry Pi if you want to, but you can buy for, let's say, $500, you can buy a fairly good gateway from a reputable supplier. If you want to go to the high end, you get the Cisco gateway, for example. The network server software there's a number of open source solutions for this. So you can build this yourself, you put it on a server in a rack, and that's it. And the application enablement environment, there's lots of options as well. So it's a very open technology. The hardware is very cheap, and so you can build your own applications. And because the chips, the Semtech chips only implement the physical layer, what we have done, for example, looking at time slotted mechanisms, etc., all of this you can build yourself. You're not tied into a particular kind of version that's developed by a manufacturer, for example. So that's very attractive, and that's why a lot of people use it. And I know a lot of startups now in Europe, for example, that are working around offering services around LoRa.
Thank you.
So, other questions, Kevin?
One further question. So,
sure.
So the devices themselves, the things you want to monitor, in our case, maybe moisture, or maybe we would want video, or some of the other things. I guess, isn't that kind of a drawback? I mean, you wouldn't want to be in all of those businesses, right? I mean, different sensors have different requirements, and it's a lot of work, right? See, maybe a gateway, if you had the sensors that were transmitting in LoRa, then it may be a different story. But in some ways, you're limited. Well,
it depends on your application. So if you're talking about moisture monitoring, for example, I would say LoRa is fine, and you can buy LoRa moisture sensors, for example. If you search for them, they'll come up. I'm not sure how available all of this is in the US, but in Europe, there are plenty of suppliers for this. So there's no problem. as I mentioned earlier, the data rates are quite limited. You
Right.
know, so we're not talking about video here. If you want video applications, LoRa is not your choice. You know, you have to pick something that is higher data rates. I guess the applications that could just about you know, a very compressed video, for example, could just about work with licensed spectrum technology like LTE-M. You know, you know, the cut one of LTE, for example, might just about work with that, but that won't be low power. The nodes won't be living on a battery for a long period of time, for example. You know, so this is the kind of rationale behind LoRa, is that the transmission is very infrequent for typical sensing applications, and the battery lifetime is quite long. You know, so moisture sensing fine, video not.
Okay, thanks.
Other questions? So Dirk, what about the security?
Yeah, so security, it's LoRa. LoRa has a private key mechanism, so you need to program the keys into the nodes, and then it uses AES encryption. I think 228 or 256-bit encryption. So it's reasonable, you know, but it's not the most secure either.
Thank you. And Johnny, you have a question.
How do you see application possibilities?
Johnny? Yeah, do you want me to read, or you can see it, right?
I can see it, yeah. So yeah, so I guess it's about connectivity. And so a weather station, I guess the data created by, you know, the weather doesn't change very rapidly, not on a per second basis. So again, the sensing, the frequency of sensing here, maybe wind, temperature, you know, humidity levels, whatever a base station might sense, for example, air pressure, would be at a rate that would be suitable for LoRa. In terms of connectivity, as I said, is, you know, we're talking about 10 miles and maybe even beyond on the spreading factor 12 in open areas. That may be possible. As I mentioned, theoretically, there are no implementations yet for LoRa on satellites, but there's a company called a Dutch company called Lacuna Space, which is working on this. So yes, absolutely. I think distributed weather stations would be possible. I've been talking to former colleagues of mine who are working on a network of weather stations around the Cork Harbour area, for example. And the Cork Harbour area is a little bit like, you know, I see in the background the Golden Gate Bridge there in San Francisco behind Sajal. And so it's Cork Harbour is the second largest natural harbour in the world. So it's a bit like the San Francisco Harbour area, which is, so there's a lot of scope for distributed weather stations as well. So that's actually underway at the moment.
Good. Other questions? So what Kevin was mentioning, actually, we have a smart agriculture proposal that we got funded last October from the Smart and Connected Communities program.
Right.
You're familiar with that. So here, the farmers, so it's a joint collaboration with Iowa State University and University of Kentucky. So our community is the farmers who grow different types of things like soybean, corn, and all these things in the state of Iowa. And these farms are very large farms, as Kevin was mentioning, like acres and all, right? So connectivity is not very good. They're very sparse and scanty kind of stuff. So our objective is how to provide rural broadband connectivity so that they can share information about weather condition is one, moisture and all, but also disease, right? And any other information that helps them to improve the crop yield. And all sorts of different things, but at the same time, how to do it in a privacy preserving manner so that they don't run into competing with each other. But at the same time, they all gain. So that's why actually we are trying to see what technology would be the right platform use, we are looking into some of the white space as well, USRP and white space. So the question, I think that Kevin was saying that, okay, compared to other technology like white space, which is abundant TV white space versus LoRa, what would be a better one if you have any thoughts on that?
Yeah, I guess that the number of considerations here. I mean, one is kind of, kind of what data, how much data do you need to transmit, how frequently, etc. So that's one consideration. The other consideration, I guess, is the available spectrum that you have, and what are you allowed to do in the spectrum. So as I mentioned earlier, here in Europe, the spectrum in which, the ISM bands in which LoRa is operates has these 1% duty cycle limitations fixed. So if you have spectrum that doesn't have that, then you can transmit more frequently, for example, maybe with a higher data rate. But ultimately, the more you transmit and so on, the more power you consume. So again, your use case, you need to consider how long do these devices have to operate on batteries? What kind of battery charges will you have available? How many watt hours, for example, etc. And then the question is, do you want to develop something from scratch, a new technology, based, from the physical layer up in order to optimize this? Or are you going with something like LoRa, which is an established technology where you get very low cost chipsets from Semtech, for example, and you can build on top of that? So I guess for some of what you mentioned, LoRa might well be a useful technology, for example. And as far as I know, is that in the respective ISM bands in the US, the duty cycle limitations are quite different. I'm not 100% sure what they are, but they are certainly not as limited as in Europe. So you have much more scope here. But again, there are lots of other technologies, connectivity solutions for the IoT at long range, for example, that you could consider. As I mentioned, is what was it again? Can't even remember the kind of, which I mentioned at the beginning, the link, is it Link Labs or whatever they're called in the US? The Link Labs in the US with their Symphony system, for example, that's building on LoRa modulation. That's already a kind of a technology that's available commercially, as far as I know, in the US. So it's certainly something to consider, depending on what, where you want to innovate, where you want to, try out new things.
Yeah, we're actually looking into that, and Kevin is researching different technology, and very soon we'll be making a decision of what would be the best one, affordable, as well as we can play with, as you said, like open source, and you can program them so that it's not very proprietary. Yeah, and reliable to some extent. Before we go into other questions, so a couple of announcements. One is that this Friday at 11 o'clock, we have two seminar series. One is this 10 o'clock on Mondays and 11 o'clock on Fridays. 11 o'clock Friday seminar this week will be given by Dr. Saptarshi Debroy at City University of New York. Not New York. I put something wrong on the chat. And the title of his talk will be Fog Resource Management for Future Smart Disaster Response, Challenges and Directions. It has a different Zoom link, which I have already put in the chat, and that's the one we use every Friday, 11 o'clock. And next Monday, 10 o'clock, the same time, using the same Zoom link, our own Dr. Sid Nadanla, our faculty, will be presenting Fair, Strategic, and Trustworthy Socio-Technical Systems. So please do attend these two talks. And now back to the Q&A session again. Other questions?